Welcome to another thrilling episode of Cosmic Wonders. Today, we're diving into one of the most intense and awe-inspiring phenomena in the universe, the collision of neutron stars. Buckle up, because this is going to be a cosmic journey filled with mind-blowing science and extraordinary discoveries. The universe is full of wonders, and the collision of neutron stars is one of the most spectacular events that occur. Imagine two incredibly dense remnants of stars locked in a death spiral, ultimately colliding with such force that it releases an unimaginable amount of energy. This event not only lights up the cosmos, but also provides a unique opportunity for scientists to study the extreme physics involved. So, what exactly happens when neutron stars collide? Let's explore this cosmic dance in detail. When stars collapse, they often leave behind incredibly dense, small remnants known as neutron stars. These remnants are the cores of stars that have exhausted their nuclear fuel and undergone a supernova explosion. Neutron stars are fascinating objects. They are so dense that a single teaspoon of neutron star material would weigh as much as a mountain on Earth. But what makes these stars even more intriguing is what happens when two of them are in close proximity to each other. If two neutron stars are close enough, they start a death spiral, gradually drawing closer and closer together due to the emission of gravitational waves. This process can take millions of years, but eventually, the two stars collide in a cataclysmic event that releases an immense amount of energy, lighting up the cosmos in a spectacular display. During this collision, the point of impact is heated to unimaginably high temperatures, creating conditions that are unlike anything we can replicate on Earth. But what exactly happens during these collisions, and what can we learn from them? Recent simulations have uncovered some fascinating insights. Penn State physicists have used advanced simulations to study these neutron star mergers. They found that during the collision, hot neutrinos, tiny, almost massless particles, are briefly trapped and remain out of equilibrium with the cold cores of the merging stars. Neutrinos are fascinating particles. They are incredibly difficult to detect because they rarely interact with other matter, passing through the Earth and even our bodies without leaving a trace. But during these neutron star collisions, neutrinos play a crucial role. For 2 to 3 milliseconds, these hot neutrinos interact weakly with the matter of the stars, helping to drive the particles back toward equilibrium. This brief interaction provides new clues about the extreme physics at play during these powerful cosmic events. By studying these interactions, scientists can gain a better understanding of the conditions inside neutron stars and the processes that occur during their collisions. This research emphasizes the importance of simulations in studying phenomena that cannot be experimentally replicated. It's like having a cosmic laboratory where we can explore the universe's most extreme environments and learn more about the fundamental laws of physics. Published in the journal Physical Review Letters, this groundbreaking research relies on simulations because replicating these cosmic events in a lab is impossible. Led by Pedro Luis Espino, a postdoctoral researcher at Penn State and UC Berkeley, the team harnessed the power of Einstein's theory of general relativity to simulate these extraordinary collisions. The team used massive amounts of computing power to create detailed simulations of binary neutron star mergers. These simulations take into account the complex physics involved, including the effects of general relativity, the behavior of matter at extremely high densities, and the interactions of neutrinos. By doing so, the researchers were able to recreate the conditions that occur during these collisions and gain new insights into the processes that drive them. The results of these simulations are nothing short of groundbreaking. For the first time, scientists have been able to see how hot neutrinos are created and interact with the matter of the stars during the collision. This has provided new clues about the physics of these events and has opened up new avenues for research. One of the most exciting aspects of this research is that it provides a new way to study the universe. By using simulations to recreate the conditions of neutron star mergers, scientists can explore phenomena that are otherwise impossible to observe. This has the potential to revolutionize our understanding of the cosmos and the fundamental laws of physics that govern it. Neutron stars are named for their composition, primarily neutrons. To understand why this is significant, we need to delve into the physics of these incredible objects. Neutrons, along with protons and electrons, make up the atoms that form all matter. In a neutron star, the density is so extreme that the protons and electrons are squeezed together to form neutrons. This process creates an object that is incredibly dense and has a gravitational field so strong that not even light can escape from its surface. Imagine a typical neutron star. It is only tens of kilometers across, yet it contains about 1.5 times the mass of our Sun. To put that into perspective, our Sun is about 1.4 million kilometers across. This means that a neutron star packs an enormous amount of mass into a very small volume. The result is an object with a gravitational pull that is so strong that it can bend light and warp space-time around it. The density of a neutron star is almost unimaginable. A single cubic centimeter of neutron star material, roughly the size of a sugar cube, would weigh about 1 billion tons. This incredible density creates conditions that are unlike anything else in the universe. When two neutron stars collide, their immense gravity pulls them together with such force that the impact heats the point of collision to temperatures in the trillions of degrees Kelvin. This heat is so intense that it can create new particles and trigger nuclear reactions that are otherwise impossible. However, because the stars are so dense, photons, the particles of light, cannot escape to dissipate this heat. Instead, the stars cool down by emitting neutrinos. This process provides a unique opportunity to study the behavior of matter under extreme conditions and to learn more about the fundamental forces that govern the universe. During the merger, neutrinos are created as the star's neutrons smash into each other. These neutrinos are then blasted apart into protons, electrons, and more neutrinos. The behavior of these neutrinos during the collision is a key area of study for astrophysicists. According to the researchers, the neutrinos created during the collision are briefly trapped by the heat and density of the merger. This out-of-equilibrium phase, lasting just 2 to 3 milliseconds, is when the most interesting physics occurs. The hot neutrinos interact with the matter of the stars, helping to drive the particles back toward equilibrium. This interaction provides new insights into the physics of these powerful events. One of the most intriguing aspects of this research is how it can impact our understanding of the signals we observe from neutron star mergers. The precise physical interactions that occur during the merger can affect the types of signals that could be observed on Earth, such as electromagnetic and gravitational waves. By studying these interactions, scientists can learn more about the conditions inside neutron stars and the processes that occur during their collisions. This knowledge can then be used to inform the design of next-generation gravitational wave detectors, which could be designed to look for specific signal differences caused by these interactions. In this way, the simulations play a crucial role in advancing our understanding of neutron star mergers and guiding future experiments and observations. The work of Espino, Radis, and their team, supported by multiple international organizations, highlights the critical role of simulations in understanding the universe's most extreme events. This research not only enhances our comprehension of neutron star mergers, but also informs future experimental designs and observations. The findings from these simulations have the potential to revolutionize our understanding of the cosmos. By providing new insights into the physics of neutron star mergers, this research can guide the development of new technologies and experimental techniques. For example, next-generation gravitational wave detectors could be designed to look for specific signal differences caused by the interactions of neutrinos and matter during these collisions. This would allow scientists to study these events in even greater detail and to gain new insights into the fundamental laws of physics. The research also underscores the importance of international collaboration in advancing our understanding of the universe. The team of researchers includes scientists from Penn State, the University of California, Berkeley, Friedrich Schiller Universität Jena in Germany, and Università di Trento in Italy. Their work was supported by funding from organizations such as the U.S. National Science Foundation, the U.S. Department of Energy, the Deutsche Forschungsgemeinschaft, and the European Union Horizon 2020 initiative. The simulations were performed on some of the most powerful supercomputers in the world, including Bridges 2, Expanse, Frontera, and Perlmutter. These resources were provided by the National Energy Research Scientific Computing Center, a DOE Office of Science user facility. The researchers also acknowledged the Gauss Center for Supercomputing EV for providing computing time on the GCS supercomputer SuperMach NG at the Leibniz Supercomputing Center. This research highlights the power of collaboration and the importance of investing in cutting-edge technology and computational resources to advance our understanding of the universe. As we continue to explore the cosmos, we can expect to uncover even more incredible discoveries that will push the boundaries of our knowledge and inspire future generations of scientists. Astrophysics continues to push the boundaries of our knowledge, revealing the universe's hidden particles and forces. The collision of neutron stars is one of the most spectacular and informative events we can observe, providing a unique window into the extreme physics of the cosmos. As we continue to study these events and develop new technologies to observe them, we can look forward to even more groundbreaking discoveries. What questions do you have about neutron stars and their collisions? How do you think this research will impact our understanding of the universe? Leave your thoughts in the comments below, and don't forget to like, subscribe, and hit the bell icon for more cosmic explorations. Until next time, keep looking up at the stars and stay curious.